that I incorporated the Hooke's law. So the reason why I did this, I just wanted to substantiate general relativity, which states that anywhere in space, the inertial mass and gravitational mass are the same. Well, of course, he had some experiments, thought experiment about the elevator. If you go into space and then there's no way you can see the outside, you cannot distinguish whether you're accelerating due to the gravity or you're accelerating, there's a rock down underneath you and goes up. So what I did on this one, on this special pendulum, as you can see, if I hold this up, you can see this spring is not extended at all. It's only 5 centimeters. But as soon as I let this go, see, it's like a scale almost. So this is extended 10 meters. But if I raise this and release, something special happens. See, as this goes easy like that, you can see this is extended all the way. But as I release it, something important happened. This bob is 327 grams. So when it reaches over here, the gravitational potential energy becomes kinetic energy back and forth. And then there is no force exerted on a spring. I will display in a minute. So you can see the inertial mass and gravitational mass are shown in this experiment perfectly. So there is no way we can distinguish unless if there is action and reaction. So the action is here. This bob is traveling all the way to here, which is kinetic energy converted to gravitational potential energy. But something important happened where the gravitational potential energy is going to convert to kinetic energy or vice versa. This is fully retracted. So it's exactly, it looks like there is no force exerted, even though this bob has a gravity, it has a mass, but there's nothing is acted on it. So I display in a minute, you can see. I raise this like this, now you watch. When it goes to the other side, you can see this is extended all the way, but when it gets to the end, when it's changing from kinetic energy to gravitational potential energy, that is retracted. See? You see what happened here? See? Well, of course, unfortunately, you can see the Coriolis effect because the Earth is rotating. So what happened? This is exerting force on my pendulum, and the pendulum is getting deflected. So I need a little bit maybe further from the wall, but you can see how it's retracted here. You see? So it's fully retracted. The reason why it's changing from kinetic energy, see now, Coriolis effect. So this Coriolis effect is so important, and like I said, I had to do it a little bit more. Oops, it snapped. As I mentioned before, mass determines the acceleration produced in a body by a given force acting on it. The mass also determines the force exerted on the body by gravity on it. So you can see this one is 1 kilogram, that one is 500 grams, and this is 250 grams. And you can see the acceleration due to gravity on all of them are the same. So determining factor here is not the acceleration due to gravity, it's the mass. So this mass is dictating gravity. I need to propel myself, like I would say maybe 50 centimeter and 500 grams dictates to gravity. I want to propel myself maybe 30 centimeters, maybe this one 20-25 centimeters. You can see how important it is, and it doesn't matter if I take this to the moon, it's going to be the same. The proportionality is going to be the same. If I take to this Mars, it's going to be the same. So the determining factor is not the gravity, is the mass, or how much the mass wants to accelerate. But this is another experiment, and like I said, in one of my theories I mentioned mass can become acceleration and acceleration can become mass. And unfortunately the humans have a problem traveling to Mars because of muscle atrophy and some of the problems in the space, even though they do a lot of workout, but sometimes it doesn't help because Mars might take 6 months from one side and 2 years back from the other side. So this seems to be the best way to have gravity, or to have weight up, I would say. See, this can be considered a spacecraft in space if it's going just a uniform acceleration. All these astronauts are the same. They are not feeling anything. But as soon as they rotate these, so what happens? You see, those astronauts are pushed against the walls. Well, I don't know how big the spacecraft is, but you can see those 3 wooden chips are like astronauts. But this is another way that, if you change the rate of acceleration in space, you can have artificial, they call it artificial gravity. This is my special pendulum, which I demonstrated a few minutes ago, and this is the Albert Einstein's general relativity. As you can tell, there is no way that you can distinguish between acceleration or gravity, and as he said, they're both the same. So this guy, this astronaut, closed the elevator, and then the elevator snapped, and it's going to fall. This one is in space, is the same way, they fall. There is no way they can tell they're accelerating due to gravity, or there's a rocket underneath, like this one is going up. So this tells you something important. The Albert Einstein general relativity. If there is no action and reaction, there is no way you can find out whether that mass is going to accelerate. And then, if I'm in a uniform acceleration like a space station, imagine there is no way that I have a mass. But as soon as I change my acceleration in the space station, I can tell which is which. And of course, I have some thought experiment. In space, there is no way, because the Earth is not pushing on you, or there is no action-reaction. Like these 2 basketball players, this is my thought experiment. Number 5 is 180 kilograms, and number 15 is 120 kilograms. And the good basketball players can jump up to 1 meter 20 centimeters high. It takes almost 1/3 of a second for them to fall. So in fact, when they fall, they are in free fall because there is no action reaction on their body. It doesn't matter how heavy they are. But as they push each other, you can see this 5 kilograms has 180 kilograms and number 15 has 120 kilograms. So they propel themselves to the inverse proportion of their masses. So this heavy person will be accelerated 1.2 meters per second on the opposite direction, and the other player will be 1.8 meters the opposite direction. Well, of course, I have some other experiment as well. Let's say these two astronauts are in a space station, and Angela is 80 kilograms and John is 120 kilograms. So they have the roller blade, and then they have a little strap to the floor. So as they are going, or they're orbiting the Earth, none of them have weight. But if they push each other, if they join their hands and push each other, you can tell the Angela is going to be accelerated more, is going to be accelerated 1.2 meters per second to the opposite direction, and John is going to be accelerated 80 centimeters to the other direction. So you can see all these things tells us something. When there is no action-reaction, it doesn't matter in space, even if I'm outside, like solar system, hyperbelt, and there is no gravitational force or anything. My spacecraft is just if I fire the engine, what will happen? I will have my action and reaction. So that is amazing. So you can see my spacecraft outside the solar system can have action-reaction, then it can feel its weight. So it's always the same thing. If you don't have any action-reaction, you cannot determine how much the mass weighs. Even on the surface of the Earth, if I'm a wrestler or boxer, I cannot compete with twice as much my weight because I cannot accelerate the other wrestler or boxer. If I punch them, my punch is not going to be so strong. But if they punch me, I will be accelerated inverse proportional to their masses. This action-reaction can happen in space. I have to mention Max Planck formula here for the photons energy. So photons energy is equal to Max Planck's constant times frequency. One of the greatest concepts in humans is solar cell, where it's something like this, almost reflective thing. When the sun's electromagnetic rays reflect on this, it gets 200% momentum and it propels this in space. And of course, this is one of the greatest ideas for the humans to propel beyond Mars and then go in some other planets. But unfortunately, the problem is we need to escape gravity. We need a lot of force to escape gravity. But this is a good idea as long as this is in space. Even though Albert Einstein said the photons have no mass. So how come something without the mass can accelerate huge, like a solar cell like this in space? How could it happen is beyond my understanding. But what I mean, this action-reaction can happen in space, can happen in everywhere, and according to Max Planck, the frequency, Max Planck constant times the frequency, so that can happen anywhere. So as long as we don't have this action-reaction, there won't be any acceleration. So the sun's the energy reflects to this surface and then gets exactly twice as much momentum and propels it forward. Some theories came true. Sir Isaac Newton did this thought experiment almost 300 years ago, but he never experimented anything. He said that in universe all the masses attract each other. But another genius, his name was Henry Cavendish, he came many years after Sir Isaac Newton, and then he did this experiment with great precision. He was a special or weird person. He did this experiment 30 times. And then that was great with precision. He realized that he has two masses like this and they were suspended. Well, of course, he had a closure so the wind won't do anything to it. Then he realized that they call it torsion balance. Then he realized what Sir Isaac Newton said many years ago, it came true. And he proved that, in universe, all the objects attract each other or they, attract each other. Yes. Another one was for the Kepler. Kepler was a great scientist. He discovered second laws of motion. The planets closest to the sun, they travel faster, like Mercury and Venus and Mars and like the Earth. And then further they travel slower. We have the same thing now after the planet, after the Earth. Now we have the space station. You see how close it is to the Earth. Then GPS, we have a little bit further. then those geostationary ones are almost 42,000 kilometer altitude, they go smaller. So we can tell this is exactly second laws of planetary motion by Kepler. So it doesn't matter if instead of sun we have Earth, but see how fast the space station is moving around the Earth or the orbiting, then the GPS, low orbit and the high orbit, they're going the same way. And another example was special relativity. They said the time dilation, and it was proven after that the Albert Einstein died in 1955. Then we were in space after 1967. Then they realized when the astronaut go into space, then they have atomic clock, so they synchronized it with the one on Earth. Then when they came back, they were 38 microsecond younger or difference. So 38 microsecond is a long time in science. So you can tell all these theories came through. And another one was George Gamow and Ralph Alper for the Big Bang. After the Big Bang it was called the cosmic background radiation. After almost 9 years, they proved that they were right absolutely. After the Big Bang, the temperature was set to 6 Kelvin, the whole universe. Then astronomer Penzias and Wilson proved that it was true, and then they won the Nobel Prize for the same discovery. So what I mean, some theories come true, but it depends on after so many years they come true. Something